September 11. Okay. Review is important today to remind us of everything that's going on. So let's start with not going all the way back to polynomial, but let me start with the logarithmic function, log. This is a function, not a notation, right? What is the domain? Best domain we can choose is as long as your input is non-zero, it makes sense, right? You can choose pi or right below the negative pi, and that's our decision. But that's kind of weird point on the negative real axis. That right on that it has argument pi, right below it is negative pi. It's kind of discontinuous. But where does that go to? What is all the complex number w in between negative pi, imaginary part going from negative pi to positive pi. This imaginary part is coming from the argument of the input. And I think I denoted this one d0 last time, right? The central strip. If you go 2 pi up there, d1, 2 pi down there, d minus 1. It's nice notation to see that. So and also I said we have lots of copies dks, right? So what is a dk in there? X plus some 2k pi, that would be fair enough. And x is coming from, well, 2k pi I, where x is complex number whose imaginary d0. So x, let me change that to w, sorry. This w is coming from d0. Make sense? W is coming from central strip, and dk denotes that you are shifted up by 2k pi units or down by 2k pi units. So that's described in the picture. Let me see. First, in the picture we have this notation. This somewhere above there's a dk, right, or below, and that is mapped under e to the z to entire complex plane. Is that right? Or not true? This whole thing under the e to the z, is that surjective? Only one point is missing, right? What was that? 0. You can't get modulus 0. Therefore, we have everything except 0 is hit. There's a one-to-one fashion. Entire strip is moved onto the punctured plane. So this backward was not capital log, not the principal branch, right? This is not going to anywhere. So we represented this process with the, what is it? lnz. lnz is not a function, it's just a notation. So I'm not going to use this functional notation in here. Not pretending lnz is a function. So best way to describe this function, maybe I should call fkz, going backward there. Looks like a function. First, you take the logarithmic, the principal logarithmic, right? That'll take you to where? The central strip, right? Then how do you get to that dk? You just move it up by 2k pi units up there, right? So if you add 2k pi, this goes up there. So description of this function as a function going from c minus 0 to the stripped dk better be notated like this, right? Not lnz. You see what I'm trying to say? lnz is just a notation of possibilities, not quite a function. It's too vague to describe this particular function. So I'm avoiding that notation. But lnz notation is very good when you solve an equation. When you solve an equation, you have to deal with the various possibility. Rather than writing all that possibility, just put it all into this notation. That's useful. So please do not use lnz when you are trying to describe a function. Function must be very, very specific. I don't know if you heard about Axiom of Choice. Mathematics and modern mathematics is all about clearly linking the chain of reasoning. All right. This one is relied on this statement. This one is relied on that. What sits in the bottom of that chain of reasoning, right? That's very important for mathematicians. An axiom of choice is kind of what is sitting in the bottom of this chain of reasoning. That is is a so-called axiom of choice. What that axiom of choice is saying is basically that when you define a function, you have to be very, very precise, nothing vague. That's what this axiom of choice is about. When you define a function, I give you a number, everybody's got to agree that what is that, what do you do to that number? For example, if I give you a subset of real numbers, and somebody says, go ahead and choose one number in that subset of real number, and someone asks you, which number? Which number do you want me to choose in that subset? And it turns out it's very difficult to describe just having that information, a subset. Have no idea how it looks like. A subset. There's no smallest element, the largest element. That choice became a big problem in number theory, not a number theory, in mathematics, the so-called axiom of choice. That goes down to some bottom of chain of reasoning that you can't explain anymore. Things like this. So here's a function. When you define a function, you have to be very clear. Everything is specific, nothing vague. So that's what I was trying to do. So that's where we are, and we define particularly f0. What's the good name of f0? Principal logarithmic branch, right? Not choosing that. f0 is not a number, it's a name of a function. So we denote it like that without z attached to it. So this is that. What was the definition of this log z? Is given by log of z. What was the definition? Do you remember that? Real part and imaginary part. That's what you have to do, right? Real part is, what is the real part? The real logarithmic on the modulus. You can't plug in 0 here, so we eliminated 0. That makes sense now. What about the imaginary part? This argument, the principal argument of pi, so that you choose pi and negative pi, and that's the definition. And we just went by, and then we looked at, sure, there's some homework problem. You did that. So let me explain a little bit here. Clearly, we have, there's a d0, right? There's going to c minus 0. Isn't that the situation under the e to the z? E to the z works on the entire plane, but if you look at the central strip, and that is one-to-one fashion. That's correct? And this particular inverse function here is called the logarithmic. Correct? So if I have a z here, and if it is going to the w, and that seems like what you're trying to figure out one-to-one fashion. Is that right? I started here, so going backwards. I choose a 1 point in the c minus 0. I want to figure out which w under the e to the z map back to the z. That's the very definition of this log inverse, right? So what is this property supposed to be? If it is w is going to z, then that's the same. E to the w is going to be z. This is what we want to solve, right? And how many such w are there? Only one in that central strip. That's why we restrict it. In overall z, yes, is infinitely many. But in that central strip, there was only one and only one, right? Okay, so that's what we're looking for in w. How would you solve such a thing? We have to write this given z as a polar form, right? How do you write a polar form? Well, it's modulus, right? Times e to the I times the argument, right? So argument is going to be theta. But we can always choose an argument. You can choose a various different argument, but you can always choose a principal argument, right? Is that right? You can choose anything that this makes perfect sense, but you can go ahead and choose the principal argument right there. Okay. This is uniquely determined. There are many choices. Whatever you put in there, this is true. Correct? Now, e to the w looks like x plus yi in there, right? Z and e to the I argument is z. Is that right? Now you separate this one into e to the x, that seems like a real number, times this. This is not theta. What is this? Y, right? So we're looking at a polar form separated length one part times the modulus. So modulus should be the same, right? So modulus should be the same. So we're looking at the equation z must be e to the x, and modulus is uniquely determined, right? When you look at these angles, they're not uniquely determined. They always differ by integer multiple of 2 pi, right? But y is coming from where? Central strip. And if you write down the principal argument, then they must be the same. There's no 2k pi I business. Okay, so here y is that argument there. Since we know y is coming from, that's our restriction, right? Where the y is only coming from the central strip, there was no other multiple possibility. They're exactly the same. So that explains why it has to be defined like this, right? Except that part. So so that's clear. Y part, that's w. That's what that w is. Y part is I times, not I times, just the angle. Sorry about this. There's no I, just the real part. Coefficient matches. So that's that. But if you solve this one, x is ln z, right? And z, absolute value of z is a positive number, so we can do that. So that explains our definition. But first, last time we just looked at it and just get used to it, not thinking about that is. All right, that's good. And then I use this notation, ln z. And this is not a function, right? It's just notation for multiple possibility. And the textbook, typical textbook, uses something called multivalued function. And I said multivalued function, confusing. So I use the example of antiderivative to get used to this notation. And I guess this morning I was walking around back and forth. I realized there's another nice way to realize this, introduced in a very clear way. You can treat this one. So what is this one? This represents the principal logarithmic plus what number? 2k pi I. Thank you. So as k varies, it is representing all the things. Why don't we just use this as a set? Z is given, and you have one value log is kz, and then you look at all that table of things. So when you do an arithmetic on there, you do the arithmetic in each individual element, just like in how the Mathematica handles lots of data, right? So you can treat it as consider it as a set. This is also very nice with the equation, so I'm going to handle it in that way. So ln z represent these infinitely many possibilities, so you can consider it as a set. If I have a set A and if I have a set B, can you make sense out of A plus B? You look at all the possibility of A and all the possibility, try to add them all, and think about all the possibility of the sums, right? And that will be what it's representing. So abusing the notation of this thing being a number and a set is not too bad. So remember, whenever you see ln z, that's you can consider it a set since it's representing possibilities, right? Okay. All right. So that's that. And what else have we been through? So also notation of z to the w. All right. Don't look at this as a z is a main variable and w is some complex constant. So this is a function z raised to the I or something like that. This is not a function, right? This notation. How did we define this notation? E to the w times ln z. Wasn't that the definition? This is what happened if z and w are real numbers, right? Correct? And because of this ln z, what does ln z represent? Infinitely many possibilities, right? It's a set. So these are infinitely many possibilities. Z to the w is representing infinitely many possibilities. So that's pretty much the end of last time, right? Tuesday class. And I also, is that right? following type of notation. The real number 2 to the 1/3, right? The meaning of the real number in 2 to the 1/3 is clear. That's the number 1.2 point something, right? Now we're introducing this notation. Whatever the complex number down there, raised to whatever the complex number down there is just no longer a number, right? What are these? These are set possibilities. So we wanted to interpret it as if you want the real number in this course, you have to specify that's the real number 2 raised to 1/3, right? Otherwise, it's going to be interpreted now as just infinitely many possibilities, potentially, right? So that's the real number. But if there's no quantifier, if I would just write 2 raised to 1/3, and not saying this is a real number, and your interpretation is that this represent what kind of number? E to the 1/3 times ln of 2, right? That's the definition. Does that make sense? This is just simply denoting third root of 2. Do you know how to calculate a third root of 2? Remember that? Square root of 1 plus I, third root of 3 plus 3i. Remember that with the Mathematica and all that? That's what that's really representing. But I'm just sticking to that strict definition of this notation. We're supposed to recover that thing that we've been doing before using this notation, right? Does that make sense? So who wants to go write it out? Here's e to the 1/3. What does this ln2 represent? It's a complex number, right? So there's a real number ln2. Maybe we should write it like this. It's terrible notation right now, but it's the real part. Wonder what is the imaginary part of 2? ln2 as a complex number, what is the argument, right? That's what we're asking. Let me write it this way. This is confusing in here. We do complex log of 2. That's kind of clear, right? That first. And plus what? 2k pi I. That's what that's representing. There's nothing vague anymore. 2k pi shows clearly what kind of possibility we're dealing with. And log 2 is a function. It's a precise complex number. Correct? So here you enter e to the 1/3. So that one is the real log in here, ln2, plus what is the argument, principal argument of this complex number 2? 0, right? Think about it, where 2 is in a complex number, that's angle 0, and plus 2k pi I, right? Is that right? Now, as you distribute 1/3, we pick up what we knew before. Since these guys are all real, right? 1/3 and ln2, that's a real logarithmic. Do you see what happens? So I'm going to first write it like this: ln 2 to the 1/3. This is allowed because it's real numbers, right? One of the advanced problem was actually challenged. You think about it in complex terms. That's that. Plus is dot, right? We proved that. E to the z times e to the w is z to the w. So what is the next part? Is 1/3 distributed there. It's 2k pi I divided by 1/3. Is that right? Okay. So as real number, and how does that simplify? That's exactly the 1/3, the third root of 2, as real number, right? Modulus. And this one, there's still possibilities, right? Because it's divided by 3, as k going through 0, 1, and 2, and 3, it is all different argument, right? Different argument. Divided by 3i. Remember when you solve a root of something, you have to throw in this 2k pi I divided by 3, or n. That one is exactly picked up by this new algebra that we're putting into this notation ln z. Does that make sense? Yeah. So what does the complex number 2 to 1/3 represent? All the third root of 2. How many are there? 3 of them. It's because that's exactly all the solutions to this polynomial equation, simply using the polynomial algebra, you can say there's only 3 numbers. That's a completely different argument. And we're picking that up using this definition of a principal logarithm and this notation on ln. We pick up that thing exactly again. Does that make sense? All right. So that's part of the homework. So we go ahead and emphasize it. Another example. This could be confusing, but book uses and all the other book uses, so you need to get used to it. So I have a square root of z squared plus z plus 1, where usually z represent complex variables, right? Now we're dealing with the complex numbers. And what is the definition of this one? This definition of this one is obviously z squared plus z plus 1, 1/2 power. If someone just loves this radical notation, they will write it like this, but that's exactly 1/2. We know the meaning of this one, right? Complex number raised to the complex number 1/2. Is this a number or a set? Given a z, is this whole thing a set or number? It's a set. Complex number raised to complex number is a set. This is representing multiple possibilities, all right? So don't use this notation, plus minus square root z plus, and they're all in where? They're all handled inside there. So there's no more plus minus root z. That's what you're going to see in the book. There are a lot of formula with no plus minus in front of root. For complex number, the root symbol is just representing all the possibilities. Does that make sense? Okay. So with this notation in hand, when you solve some quadratic equation, that would be really convenient and easy, right? But that's not what I asked you to do today in the test. I want you to really break down into real part, imaginary part. Now you got used to it. Now we have this notation. All right? Now I'm going to solve this sign property of e. We know e to the z times e to the w. Remember those? E to the z plus w, right? And e to the z raised to the integer power n, and that was e to the n times z, right? Now this e to the z, integer power is a different interpretation, right? This crazy interpretation. But as you can see, as long as this guy's an integer, you're going to always multiply integer right there, integer multiple of 2k pi. So it's not going to do anything. So and this part's still okay. We believe this is still true with a new interpretation. Is that right? Because this n is an integer. Yeah. And we proved this one using de Moivre's theorem or induction, whatever. Now, and then I didn't extend this into 1/2 or more complicated, and I was being careful, emphasizing n has to be integer and things like that. Number 3 is this log, how this log and e are interacting. The first, if you go through this log z and e, and what happened? It's going back to z. That part's okay, right? Number 4, if you do it backwards, log and e to the z, and it cuts out and into a different argument. So that is not z, right? But z times what? Z plus what? Yeah, 2k pi I. So it's better be, it's a little bit abusive notation. This is ln. Is that right? Let me see this. That's just good enough, and that's what we're going to use from now on always. All right. And I was saying before, and I thought this was a part of the homework. Was it not? This ln zw, this notation. The left-hand side is a set, right? It's a set. I'm going through all the possibility with this given zw. And ln z is also set, right? All the possibility. And ln w represent different type of possibility, and they're all together. They're infinitely many, and they're infinitely many. If you combine all of them, it's nothing more than this infinitely many possibility. As a set, they're exactly equal. Does that make sense? Yeah. Okay. It's very subtle notation. So let me give you a crazy thing in here. So don't get so here's the, if you understand this one as what is it, a set, this makes perfect sense. But if you look at it as a number, you'll be puzzled. If this is true, isn't that ln z plus ln z, right? If it is a z squared, it's a z times z, correct? It's an ln z plus ln z, right? Okay, so this is one set, not depending on the other set, right? And this is one set and not depending on the other set. Don't think that ln z is and ln z is the same number. It's two different sets. You can pick anything from there, right? So ln z and ln z could be different number if I abuse the notation. Does that make sense? So I'd like to say this is not 2 times ln z. This part's a bit crazy, because if ln z is a number, then you will say ln z plus ln z is 2 times ln z. But it's not number, it's a two sets, right? So when you write 2 times ln z, see what that represents. It represents 2 times what kind of number? How do you break down ln z of specific form? You use principal branch, right? It's log z, correct? And add what? 2k pi I. 2k pi I. So let me write it out. What do you get? There is a 2 log z that is not changing at all, right? 2 log z is function. There's no, ambiguity. But this one picks up 4k pi I, right? That's where it makes a difference. 4k pi I. This right-hand side, 2 times ln z, represent this type of number. 2 times log z, principal log, plus not 2k pi I, but 4k pi I. Okay? Left-hand side, by the way, represent what kind of set? 2 times log z, not 2 times, what do you get? Just log z plus 2k pi I, right? Let me use a different index, such as m. Isn't that 2m pi I? That's one set in one part, right? So we have log z there. You can pull something else, which is 2n pi I, right? That's the left-hand side. Correct? What happens if you add these two? You definitely always get 2 times log z, which matches the finding there, right? But what happens if you add these two? You get 2 times m plus n pi I, correct? And as a set, m and n are freely varying. And as a set, what kind of, as m and n are freely varying, what kind of indexes they cover? Every integer is covered and no more, right? You keep adding. You're just still inside the integer. So can I just write it using different index 2k pi I? It just repeat a lot, but that's just a number. Now you compare that what kind of number is in left-hand side and what kind of number is in right-hand side. This principal part is exactly the same, but this go over all 4k pi I, right? And this one is 2k pi I. These are not up there in the exponential, so they're treated as the same. They're down there, actually, in front of I, so they're really different complex numbers, right? So these two sets are not the same set. And it's easy to see. Adding two sets doesn't do nice arithmetic that you think of, right? So, because of that...
Okay, I'd like to add 2 more properties to these logarithmic function and set notation, especially the following thing is about the set notation, and it's not that pretty, so usually people don't state anything about these type of property, but it's fun to state in here and add the set notation, add sets. So the equalities we have here is not equality of numbers, but left-hand side and right-hand side is sets. The first one we have here is ln of zw's. Again, the z to the w already, this one itself is a set. For all that possibility, we're hitting this logarithmic notation, I'm not going to call this a function. Usually it's called multiple valued function. Just call this notation set notation. So set is going through this another set notation. If these are just numbers and real numbers, we usually have this w times z ln z. But if you carefully work it out, because of this ln, we have lots of 2k pi I. That is not taking care of this one. We have 2k pi I coming from here, but it's all multiplied by another complex number w's. So this additional set of complex numbers make these two things equal to each other. So if we're solving an equation, if you encounter this type of thing, we have to enter this one, and this is quite close to what we usually familiar with about this ln of z to the w. The second one is this exponential law. Now we're defining these. For example, if I look at this as a complex number, where is the w the second, w2, then we enter this type of expression. So after we enter through that, using this identity, set identity, we usually enter this type of shape. Again, if this is real numbers, we only have this part, but because these are the sets, these are the w1, this is already a large set and raised to another w2, so that's a set operate on another set. And if you look at all the possibility, is this set z to the w1, w2 multiplied by this another large set. Since w2 is a complex number, there could be infinitely many possibilities are there. So these are as a set, so these are the possibilities we get. It could be very convenient notation when we solve equation, since this equality is, allows us to handle multiple possibility with this convenient notation. But I haven't seen any of this in the literature, but I think it's a convenient thing to have.